This is part A of the gas log notes. In this video, we are going to cover an introduction to gases and modeling gases. You should be following along on the student note sheet that was provided for you. All right, so characteristics of gases. Unlike liquids and solids, gases behave differently because of those really weak IMFs. So gases expand to spontaneously fill their containers. They are highly compressible, so we can compress all those particles into small volumes. They have extremely low densities, they have indefinite shape, and they exert pressure. And so pressure meaning that in this picture here, those molecules look stationary, but those particles are actually moving around, and that pressure comes from them bouncing off the side of whatever container that they are in. As we talk about gases, we're going to have some variables that we haven't needed to discuss before that are going to impact how they behave. Our first variable that we have is moles. This is not a new to us variable, but because we're going to be working with that more often, we are going to be introduced to a new symbol for that variable, and the symbol for moles or amount of gas that we have is a lowercase n. We are also going to model the behavior of gases because the different situations that gases are in are going to change how those gases are behaving. We model gases or amount of gas with different numbers of dots. And so each dot represents a mole of gas approximately. It doesn't really matter how many dots we use in our picture as long as we're consistent in a before and after picture. So if our before and after situation required us having more moles of gas, we would show a model with less dots before to represent we have less gas and more dots after to represent that we have more gas. Our next variable is pressure. The symbol we use is a uppercase P for this variable, and pressure measures the outward push of gas molecules on their container, or we can think of it as the number of collisions of gas molecules with their container. And so that pressure comes from the fact that, again, these molecules of gas are moving around, and in that movement, they are going to hit whatever their container is. If we have a low number of collisions, then that is going to be something that has low pressure. And you can see that below. I showed with my molecules, I showed their motion, and I only showed one collision on the left. And then on the right, if we have high pressure, that means that there are more collisions that are happening. So I showed that with 1, 2, 3, 4, 5 collisions with my container, and then also collisions with other molecules. And so that is how we are going to model using arrows to show collisions between particles and the container. And we do want to consider what is the pressure inside and outside an object. Oftentimes, we are going to look at what is happening with that gas in a contained area, but it is important that we also consider if there's outside pressure and how maybe that is going to impact the object. Once we start to do calculations, we are going to measure pressure in kilopascals. The abbreviation for that is kPa. Our next variable is volume. And so because gases can fit the size of their container, volume, we use a capital V as the variable abbreviation, measures the size of the container holding the gas. Because if you have a large container, those gas molecules are going to spread out and fill that container. If you have a small container, then those gas molecules are only going to be able to go in that area. And so we are going to model that with the shape or size of a container. How we actually measure that, the unit we use to measure it would be liters. Our last variable is temperature. So temperature, we use a capital T if in a formula for that. And temperature measures the speed or kinetic energy of those gas molecules. And so if you have something that has a high temperature, it means that those molecules are vibrating or moving quickly. And so that's how temperature is a measure of that movement or that kinetic energy. How do we measure temperature? Well, when we're dealing with the Celsius system, we are dealing with negatives. And our gas relationship with the calculations are not going to show the correct relationships if we're using negatives. So when we're working with gases, we actually need to switch to Kelvin. And the Kelvin system of measuring temperature guarantees that we don't have any negatives that we are going to deal with. So we need to take our degree Celsius and add 273 in order to get the Kelvin temperature. How if we are going to model temperature of gas? We model it with an arrow length or by the arrow length to show the speed of the particle. And so a longer arrow is going to represent the molecules moving at a higher speed and therefore a higher temperature. A shorter arrow is going to represent a lower speed molecule, and so that would be a lower temperature with that. And so we can change the length. We really are looking at relative lengths, so we just want, if something's cold, we are going to show visibly shorter arrows versus longer. Or hotter, we would show visibly longer arrows. All right, and one thing to note, because we have temperature and pressure, there are conditions called standard temperature and pressure. We abbreviate that as STP. So if you're doing a calculation and a problem says the conditions are STP or at standard temperature and pressure, we use the following values. Standard temperature is 273 Kelvin, and standard pressure is 101.3 kilopascals. You do need to know those two values. They are not provided on your formula sheet. All right, so now let's go into modeling gases, and let's do some practice with what we know about modeling amount of gas, pressure, which is collisions, volume, the size of our container, and temperature, which is speed of our molecules. So using those longer and shorter arrows. A pressure cooker is used to quickly cook food by turning liquid into gas so food can cook at a high temperature and pressure. The volume of the pressure cooker does not change. Model the two scenarios below. Assume the amount of gas stays constant. And so because the volume does not change, we can see that because we have our pressure cooker is staying the same size. And I gave us an outline of a pressure cooker. If you were doing this on your own, you could always just do a rectangle to represent the pressure cooker. I don't need beautiful portraits, but we see that this stays the same size. And then the other thing that this says doesn't change is the amount of gas. So if the amount of gas is going to stay constant, that means that the number of dots that we have in our before and after are going to stay the same. And so when we're looking at these, I like to just kind of choose a dot size that is going to allow me to show enough of the relationship, but I don't want to have to do a million or address a million molecules in my drawing. And so with this, however many dots I put in my first pressure cooker, because those are staying the same, I'm going to also have that in the second one. And then we have two models. So we first have our pressure cooker at a medium temperature and a medium pressure. And so maybe this is as it's just starting to heat up. And the reason you put liquid into a pressure cooker and then when it heats up, that gets to a gas. So medium temperature means that's going to be represented in the length of our arrow. And then medium pressure, that's going to be shown with the collisions that we have of our molecules with the container. If we get to the pressure cooker at a high temperature, that means that we are going to be changing the length. We're going to want long arrows. And our high pressure, that means that we're going to want more collisions. And so as I'm looking at these, I don't need my models to kind of have the perfect length, perfect number of collisions. But if I know I'm going to have more collisions and longer arrows, that means when I look at this, I'm going to have a shorter length, and I'm going to make them relatively short just so I can compare my start to my end. And then my collisions, I'm going to only have a few because I know that I need to increase collisions later on. And so if I say, okay, I'm going to actually make my arrows pretty short over here, I do want to make it so that they kind of look the same in each of my, for each of my molecules. And then, oh, there's one collision. This, and then maybe here's another collision with the container. And so my collisions, I'm only going to have a few. This one I'm kind of showing, and if you want, you can circle those collisions. This has 2 collisions with those short arrows. If I'm going to show, this is a medium pressure, if I'm going to show high pressure, I just need to have more than 2. So we're kind of comparing both of our pictures to one another. And so with those longer arrows, we're now going to see, okay, this is longer, and you're going to see that you are going to have to kind of do more collisions in order for everything to fit. And I show maybe my molecules bouncing off the side of my container in order for those to have that longer length. We can still extend some of these really long. This one's going to bounce, and maybe this one goes this way. And so as I look, what's happening to my collisions, I needed more than 2. I've got 1, 2, 3, 4 collisions. That is more than 2, so 4 collisions is showing that that has a higher pressure. Like that. One thing you could also do is you could show a collision of maybe one molecule with another molecule. That would count. And so if I change that, that would end up to be 5 collisions to show that that has a higher pressure than our starting situation. Let's do another. And if you want, feel free to try this one on your own. A plastic water bottle is empty of liquid and normal size at room temperature. As the bottle sits outside in the cold, the water bottle gets smaller as the gas inside gets colder, so the pressure inside stays the same. Model the before and after scenarios. Assume the amount of gas stays constant. And so we have amount of gas staying constant again. And so that means we're going to have the same number of dots in our before and after. And this also said the amount of pressure stays the same. And so if the pressure is staying the same, that means that we need the same number of collisions in our before and after. What we're going to have, though, is we have our water bottle at normal size at room temperature. And so, and then in room temperature, we can say, okay, that's medium temperature. And then our water bottle crunches together in the middle to get smaller at a colder temperature. And colder temperature, we're going to represent that, remember, with our arrows. So cold temperature means I'm going to want short arrows. Medium temperature, I'm going to want longer arrows. I provided us a picture of a water bottle here. And so if my water bottle is getting smaller, I'm just showing a container that is smaller. And I do not need your pictures to be perfect because we all know I am a very bad drawer. And so when we look at this, it says it gets crumpled. Feel free to kind of make it look like what maybe a crumpled water bottle looks like. I don't know that this really represents it, but I can show, okay, this is smaller. And so now I've shown that the volume changes. This is a large volume. This is a small volume. And so now in order to get the pressure to stay the same number of collisions with the same amount of gas, it hopefully makes sense that we're going to have long arrows that are going to need to become shorter for the collisions to stay, number of collisions to stay the same. So the amount of gas, we need the same number of dots in each of these. And so as I look at it, 1, 2, 3, 4, maybe. 1, 2, 3, 4. I don't want too many because I actually made my water bottle over here pretty small. and same number of collisions. So as I start to look at that, I have medium temperature, so I'm going to have longer arrows at the start. And so I can go ahead and say, okay, here's one arrow showing temperature. Here's another arrow. I always like to make it kind of pretty obvious when my arrow collides. So there's one collision, and then we've got that there. So I am only showing one collision in this first one. So we have one collision. That represents the pressure, which means that I also need to have one collision in my other model. And so in order for us to only have one collision to hopefully make sense, we had our longer arrows, we're going to need short arrows over here so that we don't have a lot running into each other. And it doesn't have to be kind of the same dot or in the same spot. So maybe I make this one my collision. The rest of these now, with my shorter arrows, I should be able to kind of fit that so it doesn't look like those are colliding. But here's that one collision of that molecule with the bottle. And so I represented my bottle gets smaller by drawing it as a smaller volume object. The gas inside gets colder. My long arrows got shorter to represent a colder temperature. The pressure inside stayed the same. One collision in this bottle of the molecules with the container, one collision in this bottle, and the amount of gas stayed constant. I had the same number of dots here, 4 dots and 4 dots. I just chose 4. You maybe did more. I would like to see at kind of at least 4. I want you to at least fill a little bit of the space. But doing 10 dots means you're going to have to do even more arrows. And so I always think like 4 to 7 dots is kind of a good amount when we are modeling these changes. All right, that is the end of this section. You are going to come back or go to the next video for part 2 of the gas laws notes.